everyone. Good morning. How are you? Good?
Great.
Yes. We have people on Zoom. I guess we can hear you. I'm not going to monitor Zoom, but if you have questions and stuff, you can try to participate. Okay, so today we're going to talk about visualizing and understanding neural networks. And I guess by now in class, why this is not working, worked a minute ago. Oh, no, it worked. Is it working? Can we move? Okay. Okay, so I guess by now you understand from the course and history that you heard about that deep learning was a huge revolution to the field of computer vision. When I was a PhD student, I used to write algorithms line by line, and I knew each line what it was doing. But then with the deep learning revolution, it really changed. Like models became larger and larger in size or in complexity. You know, you can see the number of parameters starting from VGG16 to, ResNet. We have million of parameters, neural networks, and today we even have billions of parameters neural network. And these neural networks are becoming much more convolved in terms of their design and architecture. It's really different from being able to interpret an algorithm line by line. And so on the one hand, we saw some major breakthroughs in all these different tasks in computer vision, including, classification and recognition, segmentation, and many, many more. But with all this exciting progress, we also lost something, and that's our ability to interpret our algorithms and to understand what they are doing. And this is extremely important. You can understand that if we want to design, to use deep learning in real world scenarios and systems like autonomous driving or robotics or medical, we must understand what these black boxes are doing, and if they fail, when they would fail and why. And that generated the need to basically devise new methods that can allow us to poke inside this neural network and gain a better understanding of what they are learning, how the information they're learned is encoded inside this neural network, if they have biases of all sorts of kinds, and just in general, kind of like making these models more transparent is very important, research-wise and also for real-world applications. By the way, feel free to stop me at any point if you have questions, discussions, things that you want to say, okay? So today we're going to talk about all sorts of methods that allow us to do that. And also I'll show you, related to my talk yesterday in Fun Seminar, if you attended it, that once we gain this understanding, it opens the door to all sorts of new applications and things we can do based on this understanding and knowledge that we have on these neural networks. So let's just remind ourselves how a typical VGG network looks like. We have an input image, we have a bunch of convolutional layer where the spatial resolution is gradually decreasing. Then we have a fully connected layer, and then a linear projection on that embedding that we have to get us the final classification score, right? Looks familiar, okay? So the first thing we can do in order to, again, just the most straightforward and immediate thing we can do is actually take a look at the very first layer of this neural network, like basically here. Why we can do that? Because this layer operates on RGB images. We know RGB images. We designed in computer vision many different filters that we apply on RGB images. And these filters are no different except that they are learned. The kernels are learned, but we can visualize them and make sense of them because they operate on an RGB image. So in the first layer, what we can do, we can just grab the filters that are learned, okay? So for example, in AlexNet, what we have, I think I'm gonna basically stay here. So in AlexNet, what we have in the first layer, we have 64 different filters that are learned. Each one of them has 3 channels because, again, we operate on RGB images, and each kernel has the spatial dimensions of 11 by 11. So we can take all these filters and just visualize them as an RGB image, as you can see here. Can you tell me what these filters are doing? Can you say something about them? Or even just pick one and tell me what do you think it's doing once I take this filter and convolve it with an input image.
Kind of
Yeah. Yes.
You're searching for features, so it's like maybe you're saying like can I find this specific pattern of stripes or like the checkerboard pattern?
Yes, exactly. So these filters looks at all sorts of patterns in the image, and you can see it looks like for oriented edges and some color patterns, some color changes, and in all sorts of kinds. Some are circular, some are oriented. So it's looking for oriented edges and for certain color patterns in our RGB images, and we can make sense of it. And surprisingly or interestingly, these filters looks pretty much similar across different architectures. So it doesn't matter if we use AlexNet or ResNet 18 or other architectures, those filters are very similar in nature, as you can see here. And this shows us that, you know, the very early layers in the neural network, they tend to learn these, again, these low-level signals in our images. And this actually aligns with the seminal work of Hubble and Wiesel, and they learned vision perception. And they found that if you present a cat, there are neurons inside the cat's brain that are activated for certain stimuli of edges in different orientation. So it actually aligns with some finding and research from vision perception. Yeah.
What is it that you're visualizing in these filters? Like,
these are the filters themselves. Like the thing that you would basically convolve with an input image. Sorry, it's noisy outside. So I place this kernel on my RGB images, and I just perform convolution with this filter, which each one of them, that gives us our responses at the next layer. And you may think, okay, so let's continue and doing it for the next layer. But unfortunately, this approach won't scale up, because if we apply it on the next layer, our input is already kind of like filtered versions of our input images. They are much more high dimensional. We have many more channels, so it's going to be very difficult to make sense of it. Okay, so now let's go to the other end of this neural network. And again, what we have here, so we looked on the first layer, but if we look on the other end, think about it, that the output layer here is actually, we can think about it as a linear classifier, this layer, that operates on some vector or on some embedding. And this, we can treat the neural network up until this embedding as a function that takes as input an image and provide us this vector. And this vector is then being linearly classified using a simple projection, okay? This makes sense, what I just said? Okay. So if you think about it, if we look on this function up until here, it's doing something very interesting, because this vector, the output of the last fully connected layer, must give us a representation that will give us a very high classification score. And it must be very different from just looking at pixels at a low level, because it needs to classify all dogs together or all cats together. So it must understand something semantically about our images. So, and because it's a global vector, we can inspect it a bit. And the most simple or straightforward way of doing that would be to take a collection of images, run many images in our neural network, okay? I'm going to run many different images in our neural network. I'm going to save the output, this 4K dimensional vector for each image. And then we can search for nearest neighbors. I'm going to take one query image, compute its embedding, its 4K feature vector, compute for all the rest, and then compute some distance between them. It could be cosine distance, it could be Euclidean distance, and retrieve the closest ones and visualize them, okay? So here are some results of nearest neighbor retrieval. And you can see it's very interesting. Why? Because if you just align those images at each, so what we are seeing here is for each row, I took some query image and then retrieved the nearest, the closest images in my collection based on this similarity between those feature vectors, okay? Is that clear? And you can see that the retrieved images share the same semantic object and meaning while being very different in pixel-wise similarity. So if I just, if you look on this elephant, we get an elephant with very different poses. If we just compare pixel to pixel, we get very high similar distance. Or if you look on this pumpkin here, you can see that the very bright regions in each image appear at different locations. So pixel-wise, they're very different, but semantically, they are very similar. Okay, and these feature vectors, they are really high dimensional, right? So we cannot make sense of them easily. We can visualize things in 2D and in 3D, visualizing vectors in 4D dimensional feature space, it's impossible. But what we can do, we can basically reduce their dimensionality using dimensionality reduction techniques. Okay, so how do we do that? Again, we take a collection of images, in this case, for MNIST. Are you all familiar with MNIST dataset? Digits from 0 to 9. We're gonna take a collection of images, fit it into our network, get the feature vector in this high dimensional space, and then apply some dimensionality reduction technique to reduce the 4K dimensions to 2D. Okay? And now, dimensionality reduction techniques, I'm not going to go into the details about them. I'm just going to mention two of them. So we have PCA and Tissany. These are the most popular techniques to reduce the dimensions. And the general idea, and how they differ from one another, is what is the transformation that basically reduce the dimension. So, for example, PCA is a linear method, meaning that the projection from 4K feature vector to 2D is just a linear projection, and Tissany is a non-linear method. And they also differ in the way these methods are basically aimed to preserve the structure that we have in our data. So, for example, preserving pairwise distances between all feature points. So these methods can also differ in the way they define what is the structure among our data collections, okay? So again, I'm going to mention these two because these are the most popular. Tissany is a method that has been widely used in the context of deep learning, and I encourage you to go and read about it more. So the plot here, what are we visualizing here? So we took our collection, projected our feature vector. In this case, it was a 1K feature vector to 2 dimensions. And then we plot each point in this 2-dimensional space. And the color encodes the true label of each, the ground truth label for each image. So can you tell me what happened here? What can we see from this plot, 2D plot? What did we learn about our features? Yes.
Seems that it's like linearly separable, or at least like more or less linearly separable.
According to what?
Class.
The class. So we got a feature space that clusters images according to their label. In this case, the digit that they represent.
This is of the last layer?
This is of the last fully connected layer before the linear classifier. Okay, and this is another visualization that I actually made a while back. And here, instead of taking images from different classes, I took only images. So this is from a classifier that was trained on CFAR, has small, low resolution images of all sorts of, classes. I took images only of cars, one class. And I actually didn't look on the very last layer. I looked at conv layer 4. So this conv layer 4, it has some spatial dimensions, but I then just took this feature map that has some spatial dimension and vectorize it, and then reduce the dimension of each image using t-SNE. And what we can see here is that the separation or the proximity in this reduced space is mostly dominated by colors, right? We see on one end of this two-dimensional space red cars, and on the other side, we see mostly cars with white background. So we can see that Conv4 is mostly dominated by color. But if we go deeper in the neural network and we do the same, we can see something very interesting. We can see actually that those images and this two-dimensional space is being mostly organized or dominated by the orientation of the cars, regardless of their colors and texture and type of car that we are looking at. Okay. So again, this is a very simple techniques that can allow us again to gain a better understanding of what each layer is doing and how information is being abstracted from absolute pixel values to something more semantic until that we get in the end to this global feature vector that allow us to classify images. Okay. Next, yes.
These layers are stacked one on top of the other, right?
What do you mean?
Like from layer 9, I imagine comes after from layer
Right.
4. So
Yeah.
the information from layer 4 is lost in the way. But...
Yes. The network. You can think about it. In the end, let's assume that this model needs to classify whether it's a plane or a car. It doesn't care. It may not. It depends what are the attributes that really differentiate or discriminate a car from an airplane. Could be just the structure of the wings, and it doesn't need to care about whether it's a dark gray or yellow. Okay. Okay. So far we talked about dimensionality reduction techniques, nearest neighbors, and so on. This allows us to reason about features in a global manner. But what if we want to ask something more fine-grained in terms of localization in the image? So for example, I want to say, this is an image. It was classified as Pomeranian. It's some dog species. So I want to ask which of the image pixels mattered for this classification result? Okay, why this image, what in this image made it classified in this way? So this approach introduced TCCV 2014 by Zeiler and Fergus is a pretty simple method to answer this question. And the main idea is just, okay, let's do the following. Let's just block some region in the image. So for example, I just block this patch in the image, okay, using a square, this gray square. I'm going to fit it into my neural network and, oops, it's not, yeah. I'm going to block a region, okay, take my image with this mask, fit it into the neural network, and record the probability for this class. And I'm going to do it for all the overlapping patches in my image, as I just show you with this illustration. And this is going to give us this probability of Pomeranian for all these different regions in the image. Okay? Can you tell me what do we see here? How can we interpret this result given this image? Exactly. We can see that if I block the face region, the probability of Pomeranian significantly drops. But you see here, it drops to 0.1. But if I block some region in the background that doesn't have any information about this dog, it didn't really matter for the classifier. Okay. And here you can see the overlay of this probability map on top of the image. And we can also do it not just for the probability map, we can also kind of like grab from the neural network some channel or feature map that was mostly activated by this image. So for example, detect that layer 5 channel X was activating really strongly on this image. And then I can basically do the same thing. I can block a region and compute how much the activation in that layer changed by just maybe taking the sum over all the activation, sum over all spatial locations in order to get a scalar of how much this feature map activated. Okay, yeah.
What do you mean by activation? What do you specifically look for?
Mm-hmm.
What do you mean by activation of the layer?
Just how high the values were at the output of this layer, right? Because you have value after as your activation layer, so it must be positive. But basically, you just detect a channel in your feature maps in all layers that if you sum the values, you get a high value as output. And I guess Asaf also talked with you about that features tend to capture different patterns in the images, right? And so it basically sort of like measuring the energy that you have in a certain feature map in your neural network. And you can see here kind of like the resulting map that we get. And this allows us to see that layer 5 also cares a lot about the face of the dog. Once we block it, the activation, this layer would fire much less for this image. Okay. So here are some more examples. Here, an image of a car wheel. And you can see again that if we block the wheel, indeed, the probability of the car significantly drops. Well, but here, actually, layer 5, you can see that it doesn't really care about the car wheel, but rather fires on text. And you can see again here, another example. So the probability drops when we block the true object class, this dog. But again, layer 5 here fires on the face.
That's saying that layer 5 is more specifically targeted at finding Pomeranian or things with faces than not these other images?
No, I don't think it's more specialized towards a specific class. It detects some patterns in the image that are later processed to get us the true class. But layer 5 is, again, it's earlier in the network, so it makes sense. It won't be sensitive to a specific class, but rather a pattern. Maybe it is really being activated by faces more prominently than other layers.
Okay, so why did this paper choose to show layer 5 for these?
They did all sorts of, just to show that it's kind of like a general approach that you can also inspect intermediate representations inside the neural network and not necessarily just reason about the final classification score. Mm-hmm. Okay. Okay, so now I'm going to talk about classification activation maps or CAM. It's a very widely used technique in its generalized version, which I'll talk about also later today. And they also wanted to, they aimed to get these localized heat maps that will allow us to learn what the model is looking at. But they are doing it from a very different approach. So previously we saw how to do it by placing this occluder. By the way, we didn't talk about it, but what do you think is the problem with the occluder approach? Do you see any problematic hyperparameter that you need to tune here? Yes? Exactly, like the size of the patch that you occlude could dramatically affect the result that you would get. If the patch would be too small, it wouldn't matter for the classifier. Even if it's on the face, it might not be so important. If I take it to the extreme, if my patch is a single pixel, right? On the other hand, if I take this pet size to be too large, then I wouldn't get any discriminative regions in those heat maps. So there is this kind of like sensitive hyperparameter that needs to be tweaked and could change from one image to another. Like if you have a distant object versus a close-up object, you would get a different result, basically. Okay, so class activation maps or CAM, this is an approach that approach this goal of getting these discriminative heat maps from a completely different perspective, from an architectural design approach. So they observed that basically, if we look again on this common architecture, you know, it's before saying that, I'll remind you that in previous class, Asaf talked about it, that one of the properties that we see in neural networks in CNN is that different feature maps typically capture or are learning certain patterns in the images, right? Like, for example, as we talked about, certain feature map could detect faces. And maybe another feature map could be sensitive to tails or to other patterns that might be observed. And these are separated. So we have kernels in the end, or feature maps that would correspond separately to these different patterns in the images. You remember that? Yes. Okay, great. So what they observed in CAM is that actually we lose all this information in our neural network once we get to the fully connected layer, right? So when we have a fully connected layer, we discard all the spatial information. We just take the feature map, we treat it as one long vector and apply a linear layer on top of it. So we lost this discriminative nature of the feature maps to capture different patterns in the image, right? Questions? No, okay. So this is suggested to change this architecture in the following manner in order to preserve this property of detecting patterns by different channels in our feature maps. And here I'm visualizing, you know, the output of the last conv layer in this network. And I colored each channel at a different color, okay? So what they suggested to do is to average pool each one of those channels separately, okay? So now each of these feature map is being reduced to a single number. And then that's it. The rest is the same. You basically apply a linear layer on these average pool values to get your final classification result. Okay, so basically the score for some class, Australian Terrier, will be given by a linear combination of these average pool numbers or values. Yes?
Is it ever for the other layer or like just tension?
What do you mean? No, across all spatial locations. And you can think about it, as I mentioned previously, that you can think about it that it's sort of like the energy or, you know, a single number that quantify how much this layer was activated. And if you have, again, for each channel, this one is sensitive to heads, to tails, to some other regions, that in the end, you get a series of values that tells you how much this image was activated for each one of these patterns. And your final classification results will be given by this linear combination of these values. Yes?
What about all the other convolutional layers?
Nothing, everything is the same. You only change, instead of having a fully connected layer, you do global average pool on each of the channels, and then a linear classifier. Yes?
Yeah, but I just don't understand why the same like thought isn't. Why don't they feel like they're losing information at all? Maybe the faces, you know, one of the bigger convolutional layers where you're identifying faces. So why why do we want to lose that
No,
information?
I mean, we know by now that, that our classifier builds its representation gradually. In the beginning, you get pixel values, right? And we detect these low-level patterns in our image. If you just take a global average pool on that, you would lose all the information that you have. You need to give the network some capacity in order to build its representations, in order to abstract information it doesn't need, and to get into a representation that is more semantic and is more meaningful than just pixel level patterns. And that's why this is being done on the very last convolutional layer before we get to our linear classifier at the end. Okay? Yes.
So just instead of flattening the channels together, we do average pool for each channel, and we have one vector of number of channels numbers.
Yeah. And I'll show you. We didn't get yet to why this allows us to interpret the neural network better and to get those localized heat maps. I'll get to it in a second. But also another advantage of this architectural change is that you can think about it that you can fit into this neural network images at any resolution, right? Like it's because you it's the average pool over spatial dimensions here. It doesn't matter if this neural network is not restricted to a specific image resolution. Okay, so let's get to how do we define or how do we get our localized heat maps. So again, our classification score for a specific class like Australian Terrier would be given by a linear combination of these values like W1 times this plus W2 times this and so on, okay? So the way we're gonna get our CAM or the class activation map is as follows. We're gonna go back to our feature maps before we collapse them, okay? And we're just gonna take a linear combination of these heat maps where the coefficients for this linear combination is gonna give it through our weights of the linear classifier. So if the linear classifier weighted, the face region really high to get to this class and this one really low, we're gonna basically create a single map that's gonna average each one of those feature maps according to how much the classifier thought it's important for the classification result. Is that clear? Again, and you have to bear in mind the intuition that each one of them kind of like corresponds to a different pattern and a different semantic region in the images. And if Australian Terrier really cares about the long ears, then, and let's say that this is represented through W1 and W1 is really high, then when we create our final map, we want to take that into account. So we're gonna linearly combine the different channels from the last convolutional layer based on the weights of the classifier. Yes.
This is for analyzing the layer, the network, not for classifying images. Right?
It's both, because this method requires this change in order to get these class activation maps. So this is really a disadvantage of this approach, that it cannot be applied to arbitrary models. The model must have this average global pool before the linear classifier for this method to be valid.
Yes, but people don't use the CMAP on the network to get the output, right?
What?
But people don't use these class activation maps on the network to get the output, right?
So let's see. So actually, let's see the mathematical connection between the classifier and this class activation maps. Okay, so it really brings me to the next slide. So let's denote our feature map at some, again, at the K channel to be Fk of xy. Can you please tell me how do we denote the average, the average pooled value for this feature map? Yeah, exactly. Whoop. just the sum over all spatial locations would give us the value. And then the classification score. What would be this classification score for some class?
Like the weights might be okay.
Exactly. So the score for class C would be just WKFK, where WK is the learned linear projections by the neural network. And if we plug in again the expression for the average pooled feature, and we can rearrange the sum and actually replace the order. And what you can see that the inner expression here is what we defined as the class activation maps, right? This is the sum, this linear combination over the different feature maps, weighted by the values the classifier learned. Okay, so you can see that the final score is actually for a given class C is given to us by taking the class activation map and just partially averaging it, doing a global average pool on this feature map. Okay, and here you can see some more results from different data sets. So we're using different classifiers, and you can see actually the nice localization of regions using this approach. Yes.
Why is it still aligned? The last layer within?
Great question. So it's they're not in the same resolution, right? By the time you got to the last conv layer, you reduce the spatial dimensions by some factor. So what they've done here is just bilinearly upsample the feature map and overlay it on the image. So it's not pixel-wise aligned, but you can see that it is being roughly aligned and gives us a sense of where it activates in the image. Yes, yes.
Question for the intuition. For each class, we have the class activation. The end of why the average is the good method for deciding which class is the correct classification? Why not something that is, let's say, the strongest spot or another combination? What
do you mean, the strongest spot? I mean,
if you have in the heat map a spot that is really strong, and this is, let's say, that you are looking for specific space or in the image, then it means that it's really
activated really strongly.
Yes, activated really strong and more than the other classes.
Right.
And the average will take
no, but it's a learned average. The classifier has the freedom to learn how to blend them together. Those W1 to K, they are learned, and the classifier can decide which one of them to. Yeah. Okay. Okay. So just to say that CAM, it has some disadvantages as we discussed. It can be applied only to the last layer, and it requires architectural changes. So it's not a method we can just apply to arbitrary models. Let me continue for 10 more minutes, and then I'll give you a break, okay? So just to say that so far, we only utilize the fact that we can forward pass images in our neural network. But by now, you know that we can also backprop through this neural network and compute gradients through it. And actually, this is a property that we can leverage in order, again, to ask this question of which image pixels matters for classification. And in order to frame it in this context, we can change what, if I change my image pixels a bit, how this will affect my output classification score, okay? And in order to do that, we want to use the fact that we can backprop through this neural network. So again, I'm repeating the question that I want to ask. If I change a certain pixel a little bit, how this will affect my classification result. This is exactly the definition of computing a gradient of of a function, right? So this is a function, huge function. I have my input. Let's say that each pixels can act as a single kind of like element that I want to compute the gradients with respect to. And now I'm asking if I change each of these pixels a little bit, how my classification score is going to change. And we can compute this actually very easily using backpropagation. And I remind you that in class 2, you saw and you learned about backpropagation, right? And this was in the context of training a neural network. So basically, you computed the gradients of a certain output with respect to the weights, that neural network weights. But now, if I want to ask these questions on my image pixels, what do I need to do?
Take it with respect to the pixels.
Exactly. What do I want to do is basically compute this. Let's say I'm looking at some class L, a monkey, and now I want to ask if I change a certain pixel a little bit, how this will affect the monkey score. And the way to compute this is by computing the gradient of the score with respect to each of the image pixels. And we can do it easily using backpropagation. And if we do this, this would be the heat map that you would get. A bit disappointing because it's very spiky and noisy and so on. But this makes sense because, again, think about the occluder experiment. If the occluder is just a single pixel, then a single pixel cannot really dramatically affect our classification results in such a discriminative manner, but you can still see kind of like roughly, if you do low pass filtering on these heat maps, you can get the sense of where the object is located, right? Yes. Okay, so just to recap this part, we've seen different approaches to answering these questions of which pixels matter for classification. We saw the class activation map. The advantages is that it really gives us this discriminative, nice heat maps, but it can be applied only to the last layer and cannot be applied to, to arbitrary models. On the other end of the spectrum, we have the saliency that we can compute using backpropagation. So this approach can be applied to any existing model, and it can highlight these really fine-grained details, so because it is being computed at the pixel resolution. But it's not really discriminative because we are only changing a single pixel, and we cannot really get such a clean, nice interpretation of the model. And so we're going to take a short break, and after the break, we're going to see how these two approaches can be combined to benefit from both worlds. Okay, so please be back at 10 past 10. Thank you. Just to stress that if it wasn't clear, when we are backpropping through the neural network is trained and fixed. We're not training anything. The neural network was trained for classification. We keep it frozen, and then we just use it as a function that we backprop through it, but we don't train anything. Yes? Okay. So now again, just to remind you, so we talked about these two approaches, the class activation maps that we saw that requires this architectural change, but allows us to maintain the spatial information that the network learns. On the other end of the spectrum, we have the backpropagation based technique that allows us to reason about each pixels, how a change in each pixel would affect the classification result can be applied to arbitrary models, but it's not very discriminating. So next, we're going to talk about gradient-weighted class activation map, or in short, Grad-CAM. It's, again, a very widely used technique, even nowadays. And this method is actually combining these two different approaches. The way this is being done is as follows. We basically gonna pick some feature map in our neural network, let's say as before, the last conv layer, because it learns the most semantic information that is gonna be used for classification. And now we're actually gonna apply the backpropagation technique with respect to this feature map instead of just for pixels. So we're gonna ask how my classification score is gonna change if I'm gonna change each value in this FK feature map. Okay, I'm gonna compute this gradient here.
Again, to explain what the gradient is about?
It's exactly the same as we've done with the saliency backpropagation, only not with respect to pixels, but with respect to a feature map at some layer. Specifically, we're going to look at the last conv layer. And again, this can be computed using backpropagation. Yes.
So this is only at the very end of the network. It doesn't go.
It's a design choice. It doesn't have to be. Yeah. And then I remind you that in class activation map, we had this, score for each feature map, how much it was activated by taking the sum, the average pool values over this feature map. So here we are kind of like computing this alpha k, which has a very similar meaning. We're going to take the gradient and average it over all spatial locations. And I don't know if you see where this is going, but then, so this alpha k acts as an important weights for each feature map. If the gradients were really high, it means that this feature map was really important for the classification result, right? And now we're going to take a linear combination of our activations of these feature maps using those alpha k. We have here some ReLU that they show that it kind of like helps, but we can ignore this for now. Basically, we do the same thing as we've done with the class activation maps in CAM, taking a linear combination of the feature maps. Only here, the weights are not given directly by the linear projection of the classifier. The weights are given using these important weights that we computed using backpropagation, which means, again, that we computed how each feature map, how each spatial location in each feature map affects the classification results, and then taking the spatial average over this gradient map. Okay? And I remind you that in CAM, we had this expression that was WK times FK. And actually, it's I really encourage you to go to the paper if you want to deepen this. But in the case of this neural network, that instead of a fully connected layer, it has the structure of CAM, which is the global average pool features. It can be shown mathematically and be proven that alpha k is exactly the same as WK. Yes.
When you actually do these things and look inside the layers, most of the features and the filters things that you can actually tell what they are, or are they just like?
A very philosophical question. If the filters can tell, if we can say, I don't understand.
Like,
it's a philosophical
yes,
question.
Like you look at what some filter is doing, and you can say it's recognize. Like, is it normal that to see? We saw examples that they recognize faces. Is usually things like that, or is it usually things that you cannot really
interpret? So it depends. Sometimes you can, and sometimes you don't. But there is this tendency, and we've seen it in many neural networks. The different feature maps correspond to some patterns in the images. It's not arbitrary. It's not some, signal that you cannot make sense of. Of course, it's not. I showed you the first layers and the kernels, and we know how to interpret what they are doing. I showed you these heat maps that we can reason about, but it's not like we have a very full, detailed understanding of each filter inside this huge million parameters neural network, what it is doing. Yes? So these are all empirical analysis tools that we develop in order to improve our understanding, but we are not at the level that we can say each neuron inside the neural network, what it is doing. Actually, I'm going to talk about, again, some techniques that aim to do that, but it's challenging and it's data dependent and it's there are optimization challenges. Yes. Yeah.
Can you explain? Did we change the network here, or it's just
You tell me, did we
whatever-
change the network?
For me, it seems like
So let's-
whatever network you choose, then you
Exactly, yes. So we didn't change the network. We just computed these gradient maps using backpropagation, then take a linear combination of them. I didn't do any architectural changes. The network is fixed and frozen, and we're not training anything using this technique. And that's actually, again, the advantage of this technique over CAM. And it can be, to your question, it can be applied to arbitrary layers. It doesn't have to look on the last conv layer. And actually it doesn't even, it can look, because it's so general, it can also be used to analyze language image models. So for example, if I have this model that produces captions for images, I can use this technique with some tweaks that to highlight the regions that were important for generating this caption. You can see that it highlights on the pizza and the man. And this was important for generating this caption. Okay, so let's move on. So this so far all this method kind of and some of you mentioned it in the break, that all the method that we saw so far has been used to this is showing, sorry, some bug, ignore this, has been used to explain a given input, a given image. But what if we want to ask something much far more general, which doesn't depend on a given input? So again, now that we know that we can backprop through the neural network, it opens up the door to asking far more general questions on this neural network. So for example, we can ask, given some score, let's say, again, the score of a monkey or whatever, what is the type of image, what is the image that will maximize the score of a monkey? Right? We can ask this question. The variable of optimizations, my unknown is the input image. I don't know the input image. I want to solve for the input image. And the target is actually the classification results. I have a one hot vector at the position of the target class. So the way it's gonna look like, it's an optimization task. I want to solve for I, such that it will maximize some neuron activation. It could be some target class, it could be some other neuron if I want to. And there we have this weird term here that we want to minimize this R of I. What this R of I is some prior about how natural images look like. If we don't have this prior, and I just want to maximize some neural response, the network can cheat. It can create all sorts of high frequency patterns that will be classified as the target class, but won't look like anything like a natural image. So this would be some result that you can get. And this has a tight connection to all this world of adversarial attacks on neural network. And you will actually learn about it, I think not Wednesday, next week. So I wouldn't go into the details about adversarial attacks, but basically just to say that this RFI is a term in our optimization that is aimed to encourage solutions that look like natural images. Okay? So how the entire optimization framework is going to look like is as follows. We're going to start our unknown image with some initialization. It could be random noise, it could be some mean image, could be anything. And we're going to feed this image into the neural network. We're going to compute the score of this image. And then we're going to compute the gradient of our objective function, which is basically just computing the gradients of the score with respect to each of the image pixels. We're gonna update our image according to this gradient step and repeat. Okay? Something that I hope you all can think about how you open a Python, PyTorch, and write it yourself. And again, I should say that this natural image prior is really important. So one, naive or a very simple choice of such prior could be just L2 norm of the generated image. So I want my image to have small values. It's a form of regularization, not a very fancy one, but using even such naive prior, we can already get some meaningful results. So here you can see the results of this optimization framework for different classes. And I hope you can see that, for example, for Dalmatian, you can see some patterns of spots. You can see ears. You can see the dumbbells shape here, right? So even from this very naive prior, we can see that. And if we use a fancier prior for a dumbbell, for example, you can get these types of results. Can you guess what are these? Arms. So it can really show us that, maybe there is bias in our training data. Maybe there are not enough examples of dumbbells without arms, and the network learns to strongly correlate dumbbells with arms. And just to say again that this natural image prior spans a really wide range of techniques and priors. So on one hand, we have no regularization at all, which we've seen will produce these adversarial images that are not meaningful. On the other hand, end of the spectrum, we have really high-end natural image priors, which are actually generative image models by themselves, and I'll talk about it in a second. And in the middle, we have all sorts of hacks and tricks and handcrafted priors to improve the results. So what do I mean by learned priors or a generative model that acts like a prior? Okay, so in our optimization framework, we keep this classification network fixed, right? We're not touching it. And we try to directly optimize an input image that will give us some score. And when we incorporate a generative prior, it means that we're going to use another network. It's a deep generator network. It is also fixed, and this neural network can take in some input, some latent representation, and produce an image. It was trained to generate images. So it knows, it learned priors about how natural images look like. And it can act as a regularizer or as a prior that we can incorporate here. Yes?
I feel like you said the input is usually a one-hop vector.
The target.
The target. But for most of the training, I'm sure the network is not 100% sure. Did people try adding stochastic noise to the?
I think yes, I think so. But again, it's when you are optimizing, it doesn't mean necessarily that you will get that you will fulfill your objective function to zero loss, right? It's just this is where you want to get. It doesn't necessarily mean that in the end of this optimization scheme, you will get a zero loss objective function. It depends on the local minima that you converge to. It's a really, think about it, it's a really challenging optimization task. You have all the images of dumbbells in the world, you're looking for one. It's a many-to-one problem. So it's a challenging optimization problem. You are likely to get stuck in local minima. You are likely to get the different results from each different random initialization, or even with the same initialization, running it again and again, you will get different results. Okay. Okay, so again, so how we put this generative model in the loop, instead of directly optimizing for the input image to the classifier, we are actually going to optimize for the input to the generator. We're going to optimize the input to the generator. The generator will produce a natural image such that when I input it to the classifier, I'll maximize the score. Okay? Again, not going to go into all the details here, but this is the general idea.
Now one network.
So here there are two networks, both of them are fixed, but my objective function is only defined with respect to the classification network, not to the generator network. The generator, and I don't really have R of I. This is being implemented just by, optimizing not the input image to the classifier, but optimizing the input to the generator that produce an image that if I fit it into the classifier, I'll get the target classification score. Okay, so this entire line of works led to this idea of feature inversion. So now I'm not interested anymore in the classification score. I want to explain spatial features extracted from the network. So again, given an image, I can fit it into the neural network and extract some feature map from some layer in the neural network. And now I want to ask exactly the same question as we did a slide back. What would be the input image such that when I fit it to the neural network, I will get the same feature map? Okay? So again, my unknown is X, is the image, it's the input image. And the objective function is some basically distance metric between the target feature map and the one that would be produced by fitting X into the neural network. Okay, so we have some loss function defined between phi0. Phi0 is the feature map of the original image, and phi of X is the feature map of the my optimized image. Okay, and again here too we have some natural image prior as we did before. So a common choice would be, or the simplest choice would be just to take the L2 norm between the two feature maps. And again, a very simple regularizer in this case is just requiring a smooth image. So I want to have an image that the horizontal or vertical gradients would be small. So this term is the diff, just taking the difference between neighboring pixels in the horizontal and vertical directions and minimizing the differences. Okay. So here are the results of this optimization, where each time you apply the optimization separately with respect to some target features from a different layer. So these are the optimization results for ReLU 2, and so on. Okay. So what do we see? Help me.
What's the different values?
Just different layers inside the network. So starting from early layers to deeper layers. Yes.
So if we go to the later layers, it seems like there's more abstract understanding of the image, right?
Yeah, or we can say more specifically maybe that we see that the color information is being discarded, right? We no longer keep the high fidelity to the colors in the original image, but the overall structure of the object kind of like is maintained. From the very early layers, we can accurately reconstruct the image, right? Just from the feature responses of that image. So what can we do with it? Maybe you stare at these bananas and then you say, okay, so what? So let's see some cool applications that use this observation. And again, maybe now you're living in an era where it's really difficult to get you excited about something. But back then in 2016, it was, wow, it was, these results were amazing. So we're going to talk about how to use this observation for two tasks. One is to give a texture synthesis. So you're given an input image of some sample of, that represents the texture. We want to generate a new output image that resembles the same texture. And the task of style transfer. So we're given two images, one that represents the content and the other one that represents some artistic style. and the output will be a stylized image that combines the content from one image and the style of another image. Okay? And these two methods are just based on, backpropagation, optimization, and so on. So this is really cool. So for texture synthesis, the main idea is, again, we want to, given an input image, we want to optimize for an output image such that we will have the same texture. And the key question is, how do we define what is texture, right? So if we have some notion of texture that we can measure using the features that we extract from this neural network that was pre-trained and fixed, then we can define an objective function that you can see on the top here. We can say that we want to optimize for a new image I star such that we will minimize the texture differences between the original image and the target image. Okay? So how do we define what is a texture similarity or a texture distance? And the sum here is a sum over EL, and L runs over different layers. So we're gonna compute this distance between features extracted from different layers. And more specifically, we're gonna look at some layers, we're gonna extract some features, we're gonna build some texture representation from these features that we're gonna denote by G, GL, and then we're gonna have a loss that tries to match those GLs at different layers, okay? So maybe this illustration is a bit too elaborated, but it's actually very simple. Again, this entire branch and this entire branch is just our fixed classifier. We're gonna extract some features, compute GL on top of these features, and our objective function is just gonna be an Euclidean distance between the GLs of the original image and the target image. And the way we're gonna solve for this image, we're gonna initialize it with somehow, maybe random noise. And we're gonna feed the original image in the beginning to get the target feature maps and the target GLs, our texture representation. And then we're gonna do exactly what we've done before. We're gonna feed our output image to the neural network, compute its activations, extract those GLs, compute the gradients of the loss with respect to the output image, update the output image, and repeat. Yes?
How do you know what the texture representation is?
I don't know. We're gonna define it. That's the contribution of this work, is defining what is GL.
And you can do it with just one image? You don't need
Yes.
several images with the same texture so that
No.
you compare what's common between them?
No. So let's see exactly how we do this. And this goes back to actually a seminal work in computer vision, in classical computer vision, which is called the parametric texture model based on joint statistics of complex wavelet coefficients. So back then, in 1999, we didn't have deep learning that much in the field. So in this work, they had to handcraft some features that were, designed manually, and basically what they suggested is that texture can be represented using second-order statistics between those features. And more concretely, if you think about, let's go back to this image just for intuition. If I go back to this image for intuition, the type of textures that we are targeting here are textures that you can think about it's a stationary process. It doesn't matter, the spatial location doesn't really matter. The statistics or the characteristic of the texture should be maintained for each window that I will take from this image, right? So that's why kind of like second order statistics on some features that are extracted from these images is a sensible choice. And the way we're gonna do this more concretely is as follows. Let's assume that this is some feature map that I extracted from the neural network, okay? I'm gonna take each of these feature map and I'm gonna flatten it in the spatial dimension. So Instead of like keeping it as h by w by c, where c is the number of channels and h by w is the height and width, now we actually collapsed the h and w, flattened it, and we have a single vector. Okay, so each row in this C by N matrix is a single vector. Okay, and now we're going to compute a C by C matrix, which is called gray matrix. And each element in this matrix is going to measure the correlation between two features. Okay, so this is just the dot product between them, Fi dot J transpose. Okay, so this gray matrix capture which features activates together and which one are in high correlation or negative correlation or no correlation. So it just measures the pairwise relations between different features. Okay, and this is our texture representation. This is how we're gonna define our GL. So our objective function is just matching the element-wise these matrices between the source and target image. And we're gonna do that for several layers in the neural network. We did some ablation on how to choose that, and we're gonna see it next. But again, just to complete the overall algorithm, we're gonna initialize our output image, feed the original input image to the neural network, compute the original gray matrices for different layers, and then during the optimization, we're gonna basically take the output image, feed it into the neural network, compute the gray matrices for the different layers that we selected, compute the gradients of the loss using a back propagation, and update the input image, the output image with respect to these gradients. Yes.
So is the pre-trained CNN updated for the texture case, or is it just an arbitrary?
VGG trained on image map.
Okay.
And just to see the effect of using the loss, applying the loss on specific layers, you can see that again, as we've seen, very early layers that are close to the pixels, they don't really capture structures like large-scale semantic structures in the images. These are mostly color patterns, and we don't see actually the structure of that exist patterns that are more large scale that exist in the original image in the output image that we optimized for. And as we go deeper and deeper into the neural network, these patterns emerge.
Question?
Yes.
So if I understand correctly, a gray matrix is just dot product?
It's not just a dot product. Each element in the gray matrix is a dot product between two feature maps, such that each feature map is being flattened in the spatial dimension.
Okay, thanks.
Okay, so how we take this idea to perform stylization, artistic stylization. The idea here is just we still have the gray matrix loss that I just showed you, but now we need something that will also maintain the content of some input image, of the content input image, right? So the gap between texture synthesis and stylization is this additional loss that we're going to apply with respect to the original content image, such that the structure in it would be preserved. So we want to, let me recap. We have a content image A and a style image B. We want to preserve the texture of image B. So we're going to have a style loss using the gray matrices that I just described with respect to image B. And we have an additional loss that will preserve the layout of the content image A. And the way we're going to define this content loss is just extracting some features from some intermediate layer where color information is already discarded, and just want to match them using L2, just a feature reconstruction loss. Okay? That's it. And we have this alpha parameter between these two losses, and the different results that you would get depends on how much you weight the term of the style with respect to the term of that represents content. Okay? So large alpha would favor these types of solution, and lower alpha would favor these types of solution.
The first term.
It's just an L2. I show you, it's the same term that I showed you for the feature inversion. Just L2 between the features, pairwise. Okay. So one disadvantage of, so this is really was, again, at that time, amazing. I remember I was completely mind blown by these results. And then there was like a bulk of works that aim to do it in a feed-forward manner, because this optimization scheme is really slow. It takes a lot of time to optimize for a single output image. And you have to backprop through the networks and run this optimization for each image that you want to stylize. So the first attempt to have a model that will be feed-forward and can run this stylization, can produce stylization in real time is this work from Stanford that suggested to train a different feed-forward model for each style. Let's say I have this target style B. So the idea is to train one model that will be good for many content images, but for a single style. And the way to do that is that, again, all these illustrations are a bit bulky, but this is our fixed and pre-trained and frozen classification network. And the thing that we're gonna optimize is this style transfer network. And the way we're gonna train this is just using the same objective function that we defined for the optimization. Exactly the same. We're gonna use this network to define our loss, but this is frozen and fixed. We're just backpropping through it to get gradients. And now we are optimizing not for the output image, we are optimizing for the weights of a neural network that would produce the output image, given some content image. Yes?
The classification network is just for extracting the features?
And defining the loss. You really define the same loss. The gray matrices that I showed you and all that are defined on top of features that are extracted from this classification network.
Yeah, but which classes it takes? Like, which classes it takes?
It doesn't matter. The features are kind of like general enough for this task that it doesn't matter for which, at least for
an ImageNet.
On ImageNet, yes. Like VGG trained on ImageNet. You use it to establish your losses. So while you are training this neural network, you need to also backprop through this network. But you don't update the weights of this network. You're only updating the weights of this network. It's really similar to what I just showed you with the optimization, only we're not optimizing for the output image. We're optimizing for a neural network weights that will produce the output image. And this neural network, during training, it is trained on a collection of content images and a single target stack. So the weights of this neural network are overfitted to this specific stack. And if you think about it, the task here, it's not easy because the network has to learn how, for example, to compensate for contrast changes. If I really, bright image, I might need to be able to normalize it, to normalize its contrast and to apply the contrast of the target style image, which is not a very simple thing to do using neural network operations of convs and ReLUs, right? Like remove DC from a DC component from an image. And that actually led to an interesting observation. So in this neural network that I just showed you, they had batch norm on each layer. Okay, so batch norm performs some kind of normalization, but it is being done based on the statistics of a batch, and they learned. So in this work that is called Improved Texture Networks Maximizing Quality and Diversity in Feed-Forward Stylization, they observed that if you replace the batch norm with instance norm, you can get much faster and better quality of results. So are you familiar with the instance norm? Did you cover it in class? Batch norm, you know. Yes, you learned about batch norm. Instance norm is very easy. You don't need to learn anything. You actually just take based on a single example. So if this is the cube of, H by W, number of examples I have in my batch, and these are the channels, I just take the feature map at some channel and just normalize it to have zero means and unit variance. This is instance normalization. And they observed that if you replace batch norm by instance normalization, you can converge much faster. And so instead of letting the network learn how to do contrast normalization, they actually made it easier for the network, and they just do the contrast normalization by themselves. Okay? And that actually led to a different work that actually managed to take this observation and leverage it to have a single network that will be trained on many different styles, not just a single style. So the same neural network that can be applied to this pair of images or this pair of images and so on, or any combination of style image and a content image. And the main idea or the main observation is that we can not only reduce the contrast of the input image, we can actually apply the contrast of the stylized image for free using this add-in operation. Okay, so if my input image is X and the stylized image feature map is denoted by Y, then we can take our input feature map, normalize it using instance normalization, and then scale it such that it will match the statistics of the target style by just multiplying it by the variance of the target style and adding the mean. Okay, so this is just simple operation that allow them to design a neural network that can be applied on many different styles as follows. So let me just finish this and then go back to your question. We have the pre-trained VGG network, okay? We take this pre-trained VGG network, we extract our feature maps for the content and style images. We do this normalization that I just described this called add-in, and again, very well known. And then all I have to do is to train a simple decoder that will know how to decode these modulated or scaled feature maps to RGB. So everything that is trained is this decoder, and we can use the same losses as we've done before, but they actually, just to make it more elegant, they actually propose to a different loss that would match just the second order statistics of the stylized image instead of the gray matrix objective function. And again, this VGG network is just being used to define our loss that would be used to train the decoder. Yeah, so this works really well. They were able to train the neural network again on arbitrary styles and arbitrary content images. Highly cited paper with a very, small but important observations about the fact that the second order statistic, the mean and the variance in the feature map that are extracted from a pre-trained classification network really acts as holds style information. And they gain a lot by doing this normalization by themselves and not letting a neural network learn it, which is a really challenging task. Yes? Yes.
There are benchmark for this kind of experiments saying, okay, we got something meaningful, not just overfitted the color colors of the style or something like that? Or
So this is a great question. How do you evaluate results? Because it's an artistic stylization. So how do you, how do you know when you got it right, right? I don't think that there is like a standard. Though it's a chicken and an egg, because we defined an objective function for stylization, it would have been like the same objective function that you would use for evaluation. But we're not doing it. We don't want to have the same metrics for optimization and evaluation. So the way people are evaluating these results are typically using user studies. And these user studies can get really, non-scientific in my, sometimes in my opinion. But it depends on how large scale they are, and what exactly do you ask and how you present the results to the viewers. But in all these style transfer papers, you would see some human study about evaluating the results, because the lack of, an objective metric for evaluation. Yes.
it should be style and then content, right?
What?
It should be style and then content.
Should be, it's the other way around. Yes. Thanks. Yes.
It's, as far as I can understand, this is all based on the amazing insight that the second order correlations are the
Not only. It is based on the seminal work that I mentioned from style transfer. Second order statistics can allow on features extracted from an image can act as a powerful texture representation, but it is also based on insights and understanding of the internal representation of a classification network.
Yes, but is there a way of finding some characteristics of images by just choosing a bunch of images that you want to mimic, giving them to some network and getting the network to learn what is the style?
So
to mimic that, or is it like,
what do you
for
mean?
example, say you want to maximize like third order correlations.
Yeah.
Is it worthless because humans cannot really distinguish that?
Yes. I mean, it's a good question. How do you define style? So for example, in my lab, we wanted to target, I think it was CVPR 21. We wanted to target a different stylization task for, let's say you have dog A and dog B, and you want to transfer the texture from dog B to dog A. You can no longer represent it as second order statistics, because what I said about, the texture being stationary process is no longer correct. You must transfer it region to region. You need to transfer the color of the eyes to the eyes and ears to ears. So how do you define what is texture in this case, right? So we actually had the work that showed how you can represent style and perform this semantic style transfer task using features that are extracted from a model that was trained not for classification, but for representation learning, like in a self-supervised manner. And we had some insights about that, and then we showed how we can use that for this task. So it really depends. There is not kind of a well-defined closed form mathematical definition to what is style. I think, again, we are dealing with this question for a long time in the field of computer vision. It really depends on the use case. And I just think it's a really nice demonstration of our all the classical traditional ideas from computer vision have been modernized using deep learning. Okay, so next class, you're gonna hear about learn very useful tools in the advanced PyTorch tutorial on Wednesday. And then related to what we discussed today, Nifchaim is going to talk about adversarial examples on next Monday. More questions? Yeah.
you repeat it for the loss function, how you calculate it for the starting span?
You can come over, okay? Thank you.
Thank you.